A histogram is a graphical method for displaying the shape of a distribution. It is particularly useful when there are a large number of observations. To illustrate, we will create a histogram based on the scores of 642 students on a psychology test. The test consisted of 197 items, each graded as correct or incorrect. The student scores range from 46 to 167. The first step is to create a frequency table. Unfortunately, a simple frequency table would be too big, containing over 100 rows. To simplify our task, we group scores together as shown in the next table. To create this frequency table, the range of scores was broken into intervals, called class intervals. The first interval is from 39.5 to 49.5, the second from 49.5 to 59.5, etc. Next, the number of scores falling into each interval was counted to obtain the class frequencies. There are 3 scores in the first interval, 10 in the second, etc. The left column contains the 13 class intervals, and the right column contains the frequency count for each interval. Now we are ready to create our histogram from this frequency table. We simply need to change the frequencies into bars. We changed the frequency counts into bars of various heights, and here's the resulting histogram. The first interval extends from 39.5 to 49.5 and includes 3 scores. The interval with the most scores, 147, extends from 79.5 to 89.5. Importantly, the height of the graph at each interval corresponds to the number of scores in it. This histogram makes it plain that most of the scores are in the middle of the distribution, with fewer scores in the extremes. You can also see that the distribution is not symmetric and that the scores extend to the right farther than they do to the left. The distribution is therefore said to have a positive skew. In our previous example, the observations are whole numbers. Histograms can also be used when the scores are measured on a more continuous scale, such as the length of time in thousandths of a second required to perform a task. In this case, there is no need to worry about values falling on the class boundaries. It would be quite a coincidence for a task to require exactly 7 seconds measured to the nearest thousandth of a second. We are therefore free to choose whole numbers as boundaries for our class intervals, for example, 4,000, 5,000, etc. The class frequency is then the number of observations that are greater than or equal to the lower bound and strictly less than the upper bound. For example, one interval might hold times from 4,000 to 4,999 milliseconds. Using whole numbers as boundaries avoids a cluttered appearance and is the practice of many computer programs that create histograms. Note also that some computer programs label the middle of each interval rather than the endpoints. Histograms can be based on relative frequencies instead of actual frequencies. Histograms based on relative frequencies show the proportion of scores in each interval rather than the number of scores. In this case, the y-axis runs from 0 to at most 1. You can change a histogram based on frequencies to a histogram based on relative frequencies by A, dividing each class frequency by the total number of observations, and then B, plotting the quotients on the y-axis, labeled as proportions. To summarize the steps in constructing a histogram, you first calculate the range of scores by subtracting the smallest observation from the largest. The range of scores is then broken into intervals, called class intervals. Next, the number of scores falling into each interval is counted or tallied to obtain the class frequencies. Finally, the class frequencies are represented by bars. Let's look at another example. Since this example has only 20 numbers, it is easier to see the relationship between frequency and height of the bars in the histogram. The data shown in this table are the times it took one of us to move a computer mouse over a small target in a series of 20 trials. The times are sorted from lowest to highest. The variable time to respond is a continuous variable. With time measured accurately to many decimal places, no 2 response times would be expected to be the same. As you can see from this table, no two were the same. As a result, an ungrouped frequency distribution would be uninformative. It would consist of the 20 times, each with a frequency of 1. To understand the relationship between frequency and the height of bars in a histogram, place one tally mark in the appropriate row for each frequency. Notice that the class interval with the highest frequency, 600 to 700, has the highest tally height, 6. Then, if you rotate this table on its side, you can see a figure that is beginning to look like a histogram. Finally, if you replace the tally marks with thick bars, you have a completed histogram. Notice that the highest frequency, 600 to 700, has the highest bar, just like it had the most tally marks.